What do you call a pirate with 2 eyes and 2 legs? A rookie. Why did pirates cover one eye? Some people suggest that pirates wore eye patches simply because they had one eye missing. Others, however, think that it gave them better visual acuity when swapping from light to dark. They could swap the patch to reveal their dark eye when heading below deck or fighting at night, and swap it back for daylight activities. However, this begs the question, would a pirate's motor ability have been affected by only receiving information from one eye? Building on this, we wondered how covering one eye might affect a person's ability to carry out simple motor tasks and whether they would need a larger amount of time to process incoming information. So what happens to our visual and motor capabilities when we only have access to the visual information from one eye? Binocular vision has many benefits and advantages, especially when performing tasks that require the smooth integration of visual input and motor coordination, such as reaching, grasping, and pointing. To test the effect that forced monocularity has on visual and motor ability, we carried out an experiment on a convenience sample of 4 female participants using the Fitt task. All 4 of our participants were right-handed and right eye dominant, with natural or adjusted 20/20 vision. We thought eye dominance would help with 2 things: describing our sample and increasing the effect of monocularity on the Fitt task by removing a greater amount of visual input. We assessed eye dominance in our participants by using a simple test found online. Initially, we carried out the Fitt task with both eyes uncovered to provide baseline results for later comparison. 5 rounds of 6 different levels of the Fitt task were randomly presented where difficulty was measured in bits of information. Our levels were 2 bits, 2.5 bits, 3 bits, 3.5 bits, 4 bits, and 5 bits. We used an online generator to randomize the order of the 30 trials for each participant. We thought randomizing the trials would be best as the Fitt task is of a repetitive nature and we aim to minimize any practice effects. Participants were seated at a table in a quiet room next to a large window providing consistent natural light. They were instructed that no parts of their body should touch the table and were given the same pencil for each trial. The Fitt task was presented on white A4 sheets of paper, which were stuck to the table with blue tack to ensure that they would not move. Participants were told to tap each circle of the Fitt task with the pencil as quickly and accurately as they could, and say stop when they touched the last circle. If the participant missed more than 1 circle in a single trial, they were required to repeat it immediately. One team member used a stopwatch to timekeep and inputted the data straight into an Excel spreadsheet. Another team member was responsible for changing the sheets of paper over for each level of the task, and for making sure that circles were not missed. This process was used for each participant to complete 18 trials, rest for 2 minutes, and then complete the remaining 12 trials. Following a 15-minute break, the experimental procedure was replicated with the right eye completely covered using a black plastic eye patch secured with an elastic cord. To keep with the theme of our initial group discussion, we decided to keep our hair off our faces with pirate bandanas. To show the results of our experiment, we have provided 4 graphs illustrating each participant's individual performance. These graphs show the average time each participant took per target, which was measured in seconds and plotted against the differing levels of bits. The results of the Fitt task with both eyes uncovered are plotted in blue, and the results of having one eye covered are plotted in red. A regression line can be seen to illustrate the linear nature of the results. It seems that as difficulty in bits rose, so too did the average amount of time taken per target. High R-squared values in all cases indicate that the regression line and linear equation were a good fit for the data. Lower R-squared values can be seen across all cases for the monocular version of the task when compared to the binocular version. Looking at the graphs, we can see that as the bits in the Fitt's task increased, the time per target also increased. This was the case for both the baseline and the binocular condition, and our experimental monocular condition. Further, under the monocular condition, the rate of processing in seconds increased more rapidly than in the binocular condition. The red slope of the manipulation has a steeper gradient than the blue slope of the baseline. To further illustrate our results, a table has been included to illustrate the numerical values of the intercept, slope, and rate of information processing calculated for each participant. In all cases, the numerical value of the gradient of the regression line increased between conditions, reflecting the steeper red line we see on each graph. In the calculated information processing rate column, displayed in bits per second, we see a reduction from the binocular to monocular condition of 28% to 41%. This indicates that our experimental condition considerably reduced the overall speed of our participants' visual information processing system. In addition to the numerical data we have collected, it is important to note some subjective feedback from our participants. The participants noted feeling fatigued following the first experiment, perhaps due to the repetitive nature of the Fitt's task trials. Under the monocular condition, however, fatigue was subjectively worse, with all reporting feeling particularly drained following their one-eyed trial. Participants' head movements were observed to be more pronounced as they attempted the Fitt's tasks in the monocular condition, and more trials had to be repeated due to inaccuracy under the monocular condition. It was also noted that the half of the page furthest from the uncovered eye were harder to focus on, as the Fitt circles on the left-hand side disappeared from the peripheral vision of the left eye. As previous research has shown us, binocular vision plays a key role in our daily lives. Not only is it extremely important in our perceptions of both depth and motion, but it also has an integral part in terms of our ability to seamlessly perform everyday physical and motor tasks. Research into the visual capabilities of people who have lost an eye show approximately a 25% loss in visual field area, specifically peripheral vision. They often experience reduced visual acuity due to a lack of binocular information, and issues with aiming and focusing may impair spatial orientation. Changes like these often manifest as difficulties with hand-eye coordination, frequent spatial perception errors such as bumping into people and objects, trouble using stairs, issues with driving ability, participation in sport, and various other day-to-day activities. Researchers have found that the magnitude of the impact of losing an eye can lessen over time, and have suggested that a return to feelings of normal function can occur in anywhere from 1 month to 1 year following trauma. Evidence of neuroplasticity in the visual channel of the remaining eye exists. However, the input from the visual field is still limited, and as such cannot replicate the field of view seen in people with binocular vision. The collection and analysis of data from our Fitt's task enabled us to measure the effect that monocular vision has on the speed of the brain's information processing, and retrospectively to observe the difference in fatigue between binocular and monocular vision. Our research highlighted that the speed at which we are able to process visual information of increasing complexity is significantly reduced under forced monocularity. The results are in accordance with Fitt's law of information processing, suggesting a linear relationship between the amount of visual information provided and the time it takes the brain to process it. Individual differences, such as levels of motor coordination, reaction time, central and peripheral processing speeds, to name a few, inevitably play a role in differences between results. However, similar increases were seen from the binocular baseline to the experimental monocular condition across all participants. The uniformity of the results suggests that the changes observed arose as a result of the manipulation participants were subjected to. Lastly, participants' head and body movements were greater in the monocular version of the experiment, where little head movement was seen in the binocular experiment. This may in part provide an explanation as to why increases in average time per target, contingent on increasing bits, was reflected in our results. Our results best reflect the immediate effects of losing sight from the non-dominant eye, either by choice, in the case of our pirates, or for someone who has experienced monocular trauma. The effects of forced monocularity are immediate and significantly affect our visual and motor capabilities. Forced monocularity reduces the speed at which we are able to process visual information and may additionally increase subjective feelings of fatigue. Although prior research suggests that deficits in fatigue may lessen over time, monocular vision requires a period of adjustment, and subsequent adjustments to lifestyle must also be made. Despite a small sample size, we are confident that the overall findings of our experiment would generalize to a wider population of people with 20/20 binocular vision. Future directions for research may include replication of this experiment, including participants who have been living with monocular vision for a substantial period of time, and to compare and contrast these results with data collected from temporarily monocular participants such as those seen in our sample. This would allow researchers to see if visuomotor speed and ability increase following an adjustment period. Would voluntarily obstructing the eye for dark adaptation outweigh the immediate risks of monocularity? Tasks involving spatial orientation, depth perception, and peripheral vision, such as balancing on deck, climbing ropes, reading maps, and sword fighting, would have been extremely difficult immediately following the obstruction of one eye. Maybe the pirate's life isn't for us after all.